This video is going to look at two more optimization problems. And the first one we have here, we want to find two positive numbers that satisfy the given requirements. The product is 185 and the sum is a minimum. So once again, you may want to stop the video and see if you can come up with the answer on your own. Now, we have the product is 185 and the sum is a minimum. So that means our primary equation is we're looking for the sum is a minimum. So that's going to be that primary equation. So the sum is our primary equation. So the sum is equal to, and again here it says two positive numbers. So we could say the sum is equal to x plus y. So from here we can figure out the secondary equation, because notice here we now have x and y. We want to eliminate one of these, so our secondary equation would be what they tell us here about the product. The product is 185. So we want to figure out what two numbers that we can multiply together, the product, to equal 185. And when we add the two numbers together, we will have the smallest sum. So we need to eliminate either the x or the y. So I'm going to take our secondary equation, and it doesn't matter which one we solve for in this particular case, since we're adding just x and y together. So I'm going to solve for y. So divide by x, we would have 185 divided by x. So then we can take this 185 over x and substitute that in for y. So s equals x plus our y, which is now the 185 over x. So there's our primary equation, and it's only in terms of one variable, x. All right, so now I know we need to find our critical numbers, so that means we're going to have to take the derivative. And before we do that, I'm going to rewrite this as x plus 185, move the x to the top so it becomes to the negative 1. So now it'll be a little bit easier to calculate the derivative. So the derivative would be 1 minus 185x to the negative 2. And I think it'd be easier here at this point. We want to set this equal to 0 and solve. So I would think of this as 1 minus 185 over x to the positive second power. And now from here, we want to get x squared off the bottom, so we could multiply everything by x squared. So we're left with x squared minus 185 equals 0. Move over the 185, so that's a positive 185. And now we're going to take the square root, so x is equal to plus or minus the square root of 185. Now, the original problem says we want to find two positive numbers. So that means we can eliminate the negative. So x is going to be equal to the positive square root of 185. This will be our critical number. And once again, we're pretty certain that's going to give us our x value for where we're going to end up with this minimum sum that we're looking for. But keep in mind, we want to verify this, and we can hopefully do that by finding the second derivative. So we're going to take s double prime. So the derivative of 1 over here would be 0, and then negative 2 times negative 185 is a positive 370 x to the negative 3. So that means we would have our second derivative would be 370 over x cubed. And keep in mind, we now want to look at this when x is equal to the square root of 85. Well, if you plug this in for x, you're going to get 370 over the square root of 185 cubed, and we know that the second derivative is going to be positive. And that's all that we're concerned with. Because it's positive, we know our graph is going to be concave up. And if the graph is concave up, that tells us that our x value here is giving us our minimum. So that tells us our minimum, our sum, will be minimum when x is equal to the square root of 185. So then we can always find our y value. So y is going to be equal to 185 divided by the square root of 185. Okay. So we end up with 185 over the square root of 185 for our y value. So that means our two numbers would be x is equal to the square root of 85, so the sum is equal to the square root of 185 plus our y value, which is 185 over the square root of 185. So there's our two numbers that if we multiply together, their product is going to be 185, and when we add the two numbers together, we're going to have our minimum sum. That's going to give us the smallest sum of two numbers added together that multiply to 185. Okay, the next example says we want to find the length and the width of a rectangle that has a maximum area with a perimeter of 100 meters. So right off, what are we trying to maximize? Well, we're trying to maximize the area of our rectangle. Okay, so that'll tell us right off that our primary equation is going to deal with area, and since we're looking at a rectangle, the area of a rectangle would be the length times the width. Okay, now if we're trying to maximize this, we want to know what's going to be the largest for L and W. Well, they also tell us for our secondary equation that the perimeter is 100 meters. So we know the perimeter is equal to 100. Well, we know that 2L plus 2W is equal to the perimeter, right? 2 times the length plus 2 times the width. So if we have our rectangle, we know that we have our length and our width. So we can simplify this by saying 2L plus 2W is equal to 100. And once again, our primary equation has two variables, so we want to eliminate either the L or the W. And it doesn't matter over here what we solve for. I'm going to solve for L. For this example, you certainly could solve for W. So we have 2L is equal to 100 minus 2W. And if we divide everything by 2, we get L equals 50 minus W. So that means we can take 50 minus W and substitute that in for L. So for our primary equation, we would then end up with A equals, we have the W, and then the length is 50 minus W. So now our primary equation is in terms of one variable. So once we have the equation, we can now actually distribute the W, and that'll make it easier for us to find the derivative, and we have to find the derivative so we can calculate our critical numbers. So if we take the derivative here, the first derivative would be 50 minus 2w. Set this equal to 0. We can solve for w, so we would have negative 2w equals a negative 50. So w is equal to positive 25. So once again, we're pretty sure that this is going to be the value for the width that's going to, in this case, maximize the area of this rectangle. But remember, we need to verify this. And we can verify this by taking the second derivative, which up here we have 50 minus 2w, so the derivative of negative 2w would simply be a negative 2. And if we look at this, there's no other variables, so this is very easy. When w is equal to 25, what about the second derivative? When w is equal to 25, clearly the second derivative is going to be negative. In this case, because this is a constant, your second derivative is always going to be negative, and because it's negative, we know it's going to concave down. So since our graph is going to concave down, we know that our critical number here of 25 would give us a maximum value. Okay, so we know that when w is 25, what is going to be the length? Well, we can go up here to our secondary equation. We solve for the length already. Length is equal to 50 minus w, so we could plug in and get 50 minus 25, and we find the length is also equal to 25. So w is 25, the length is 25, and let's see, I forgot our units. Our units was meters, so we're looking at 25 meters for the length and 25 meters for our width. Now, if we wanted to know the actual area, then we could just simply multiply 25 times 25, and we would end up with 625 meters squared. And you will realize that if you're ever looking for the maximum area here for a rectangle, unless you have other restrictions, the way you're going to maximize the area of a rectangle is if you actually have a square. Now, there could be other situations where if you don't have a square, I mean, they might give you some kind of restraints, but if there's no restriction with your rectangle, you're always going to maximize the area when you have a square, where the length and the width are the same, because you're going to maximize that product of 25 times 25 when you have the same number, in this case, to get 625 square meters.